Here comes the sky.
In this lesson, we're going to learn how to further describe quantities of simple harmonic motion. We have already covered what simple harmonic motion is and how to identify it. So once we identify it, how can we represent it? Our essential question driving us will be, how do we describe simple harmonic motion in terms of motion quantities we already know? In this lesson, we're going to be able to describe simple harmonic motion qualitatively and quantitatively in terms of displacement, velocity, acceleration, momentum, force, kinetic energy, potential energy. If you remember, those are all the graphs that should show up as sinusoidal when graphed as a function of time. Quantities of simple harmonic motion, displacement, velocity, just what I just said, right? Quick review. If an object oscillates, it repeats motion between two endpoints. If an oscillation is simple harmonic motion, then the oscillation has special properties. One, force versus displacement is a line through the origin, directly proportional. The endpoints are equal distance from the equilibrium, and the endpoint to equilibrium distance are called an amplitude. The graph of a displacement versus time is a sine graph. The period is independent of the amplitude. Here we've got an animation, if I will get out of the way, of three objects undergoing a vertical simple harmonic motion. The left side has a sphere that's blue with a displacement vector labeled x. Displacement is a vector that points from the equilibrium to the object's position. The center sphere has a green velocity vector labeled v. The right sphere has a red acceleration vector labeled a. Note that there are also energy bar charts shown. What can we learn from this animation? No energy is being lost to the environment, right? There's no dissipated energy. We don't have any damping happening. We also see that the bigger my displacement is in the upwards direction, the bigger my acceleration becomes in the opposite direction. And remember, force and acceleration are directly proportional. So that means my acceleration and my displacement are also directly proportional, just with opposite directions. At the equilibrium point, we have the maximum velocity and zero acceleration. At the equilibrium point, we have zero displacement. And at either of the two endpoints, we have a minimum velocity, zero velocity, and maximum acceleration because we're changing directions. When is the speed the greatest? It's always at the equilibrium. If you were asked when the object has the greatest magnitude of momentum, you would also say at equilibrium because momentum is proportional to velocity, P equals mv. When is the acceleration the greatest? At the endpoints and zero at the equilibrium. All of that is, I believe, what I just said. Simple harmonic motion is a hot potato game between kinetic energy and potential energy. The energy keeps going back and forth between kinetic and potential energy, but if there are no energy losses to friction, then the total energy stays the same. The kinetic energy is greatest at equilibrium because that's where your velocity is greatest at equilibrium, and K equals 1/2 mv squared. The potential energy is greatest at the endpoints, which is also when the displacement is the greatest. Displacement for a spring, for example, is 1/2 kx squared. If it were truly vertical, then your displacement is also going to be mgh for gravitational potential energy. So if the total energy for this situation is 1/2 mv squared plus 1/2 kx squared, and that stays constant, then the farther points from the equilibrium, the object will move slower, so it has less velocity to keep this equation balanced. Exactly halfway up, they have exactly half of each types of energy.